Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 4, Drag and Aerodynamic Efficiency. When people first learn about flight, lift gets most of the attention. That makes sense. Lift is the force that makes a heavy machine capable of leaving the ground. But in practical aircraft design, drag is often the force that determines whether an aircraft is useful. Drag determines how much thrust an aircraft needs, how much fuel it burns, how far it can fly, how fast it can cruise, and how much payload it can carry. It affects runway performance, climb capability, battery endurance, engine size, operating cost, noise, and emissions. A great deal of aircraft design is simply the effort to remove drag where it is harmful and accept it where it is useful. Drag is the aerodynamic force that resists an aircraft's movement through the air. In ordinary flight, it points generally backward, opposite the aircraft's path through the air mass. It is not one single physical phenomenon. It is a collection of different effects, each with its own cause, and each becoming important under different conditions. This lesson explains the major kinds of drag, why a wing creates drag simply by making lift, why aircraft have a most efficient speed, and why a glider, airliner, fighter, and small drone can all look so different even though they follow the same physical laws. Drag is the cost of moving air. Any object moving through air has to push that air out of the way. The air resists. This is not because air is especially sticky or because the object is somehow fighting the wind in a human sense. It is because changing the motion of air requires force and energy. A hand held outside a moving car is a good example. Hold your hand flat into the wind and you feel a backward push. Turn your palm sideways and the force decreases. Cup your hand or spread your fingers and the force changes again. Your hand is interacting with airflow through its shape, surface area, orientation, and speed. An aircraft does the same thing, just more deliberately. Its fuselage parts the air. Its wings guide air over and under their surfaces. Its landing gear, antennas, engine nacelles, sensors, doors, scenes, and control surface gaps all affect the flow. Even a very clean aircraft leaves a disturbed wake behind it. That disturbance represents energy transferred from the aircraft to the air. The engine, propeller, rotor, or other propulsion system must replace that lost energy if the aircraft is to maintain speed. In the simplest operational terms, more drag requires more thrust to hold a given speed. More required thrust usually means more fuel flow or more battery power. More power consumption reduces range or endurance. Lower drag improves efficiency, provided the design does not create unacceptable penalties elsewhere. For conventional aircraft, the total drag is usually discussed as the sum of two broad categories. Parasite drag, the drag associated with moving an aircraft's shape and surfaces through the air. Induced drag, the drag associated with producing lift with a finite wing. This is not the only possible classification, but it is the most useful one for understanding aircraft performance. NASA describes induced drag as drag due to lift, occurring on finite lifting wings, while total drag can be represented as baseline or zero lift drag plus induced drag. 1-2. The two categories behave in almost opposite ways as speed changes. That fact creates the central drag trade-off in aviation. Parasite drag, the cost of the aircraft's shape. Parasite drag is all drag not directly caused by producing lift. The name can sound insulting, as if it is useless or avoidable. In reality, much of it is unavoidable. An aircraft needs a fuselage to carry people or cargo. It needs engines, a cockpit, landing gear, antennas, cooling inlets, access panels, windows, lights, and other systems. Every one of those features can add parasite drag. The main forms of parasite drag are skin friction drag, form drag, and interference drag. Skin friction drag. Skin friction drag comes from the friction-like shearing action between moving air and the aircraft's surfaces. Air touching the surface of a wing or fuselage does not slide freely past it. Because of the no-slip condition, the thin layer of air directly against the surface is nearly stationary relative to that surface. Air slightly farther away moves faster. This difference in speed creates shear in the thin region next to the aircraft called the boundary layer. The more surface area an aircraft exposes to moving air, the more opportunity there is for skin friction. This is why a very large aircraft can have substantial skin friction drag even if its shape is streamlined. Surface quality matters too. Smooth paint, flush fasteners, tight panel fit, clean joints, and well-maintained seals help reduce skin friction. Rough paint, dirt, bugs, frost, ice, peeling tape, protruding fasteners, and damaged surfaces can increase it. At first, it may seem surprising that something as small as insect residue could matter on a wing several feet wide, but aerodynamic flow can be sensitive, especially near the leading edge where the boundary layer begins. Small roughness can cause the boundary layer to become turbulent earlier than intended, increasing skin friction and sometimes reducing the wing's resistance to separation. Engineers often distinguish between laminar and turbulent boundary layers. A laminar boundary layer flows in relatively orderly layers. It tends to have lower skin friction, but it can be more vulnerable to separation when it encounters an adverse pressure gradient. A turbulent boundary layer contains mixing and small-scale disorder. It has higher skin friction, but the mixing brings higher energy air closer to the surface, which can help the flow stay attached longer. This produces an important trade-off. A design might preserve laminar flow over part of a wing to reduce friction drag in cruise, but if the flow becomes turbulent, the wing may pay a drag penalty. On the other hand, an aircraft may intentionally use turbulence-promoting devices in some situations to help delay separation. Aerodynamics is rarely about making one property universally good. It is about choosing the right compromise for the mission. Form drag, also called pressure drag, comes from the pressure difference between the front and rear of an object. When air approaches a streamlined shape, it can remain attached and gradually return toward the object's rear. When air approaches a blunt or poorly shaped object, it may separate early and leave behind a broad, swirling wake. The pressure in that wake is lower than the pressure at the front of the object. The higher pressure on the front pushes backward more strongly than the lower pressure behind can push forward. The result is drag. A teardrop shape is an intuitive example of low-form drag. It has a rounded front that gently divides the airflow and a long, tapered rear that allows the flow to slow down and recombine gradually. A flat plate held broadside to the wind has high form drag because the air separates abruptly, leaving a large wake. Aircraft fuselages are designed to reduce form drag, but they cannot be perfect teardrops. They must accommodate people, cargo, engines, landing gear, control systems, windows, pressurization structure, and sometimes military equipment or surveillance payloads. The final shape is a compromise between aerodynamic cleanliness and useful internal volume. Landing gear provides a particularly visible example. An exposed wheel, strut, and brake assembly are mechanically useful but aerodynamically untidy. In a fixed-gear training aircraft, the added drag may be accepted because the design is simple, inexpensive, durable, and easy to maintain. In a fast business jet or airliner, retracting the landing gear after takeoff is worth the complexity because the drag penalty of leaving it exposed would be too large. A camera pod under a drone, an antenna on a communications aircraft, or a weapon mounted under a fighter wing all create form drag. Designers often add fairing streamlined covers to make these necessary features interact with the air more gently. Interference drag. Interference drag occurs where airflow from different parts of the aircraft meets and interacts. The wing fuselage junction is a classic example. Air moving around the fuselage meets air moving around the wing. Their pressure fields and boundary layers interact, often creating extra turbulence and separation that neither part would produce alone. Other common sources include engine pylons attached to wings, landing gear struts and their attachment points, horizontal and vertical tail intersections, external fuel tanks and stores, antennas, probes, cameras and sensors, flap tracks and fairings, door seams, panel gaps, and access hatches. Interference drag may sound minor, but modern aircraft design pays close attention to it. Small changes in fillet shape, the smooth blending material at a junction, can improve airflow. A carefully shaped wing root fairing may reduce drag without changing the wing or fuselage itself. This is one reason aircraft that look visually smooth often perform better than aircraft assembled from individually optimized parts. Aerodynamic efficiency depends on the whole flow field, not just the quality of each component in isolation. Why parasite drag rises so fast with speed? Parasite drag generally rises approximately with the square of airspeed. Double the airspeed and, all else equal, parasite drag becomes roughly 4 times larger. That relationship comes from dynamic pressure. whereas dynamic pressure is air density and is airspeed. The faster an aircraft moves, the more rapidly it has to push air aside and the more energetic the airflow becomes. A modest increase in speed can therefore require a large increase in thrust. There is an even more important consequence. The power needed to overcome parasite drag rises roughly with the cube of airspeed. Power is force times speed. If drag rises with the square of speed and the aircraft is also moving faster, the engine must deliver energy at an even faster rate. This is why just fly a little faster can be expensive. For many airplanes, a small increase in cruise speed may require noticeably more fuel per hour. The aircraft does get there sooner, so the fuel used per trip does not always rise in the same proportion, but speed has a real operating cost. This is also why high-speed aircraft need powerful engines and why sleek shaping matters so much. A fighter designed to operate near or above the speed of sound cannot simply be a normal airplane with more engine power. Its fuselage, wing, inlet, canopy, engine installation, and external stores must all be designed with high-speed drag in mind. For a battery-powered drone, the penalty can be especially severe. Batteries store much less energy per pound than aviation fuel. High parasite drag means high electrical power draw, which quickly reduces endurance. That is why a long-endurance fixed-wing drone often has a slender fuselage, smooth surfaces, carefully integrated antennas, and a propeller sized for efficient cruise rather than aggressive acceleration. Induced drag. The cost of making lift. Parasite drag is the cost of moving the aircraft's physical shape through air. Induced drag is the additional drag created because the wing is producing lift. At first, this can sound backward. If lift points upward, why would producing lift create a rearward force? The answer lies in the three-dimensional nature of a real wing. A theoretical wing of infinite span would have no tips. In that idealized case, the pressure difference between the lower and upper surfaces could remain uniform from one side to the other. A real aircraft wing has tips. Beneath the wing, pressure is relatively higher. Above the wing, pressure is relatively lower. Near each tip, air naturally curls around from the high-pressure underside toward the low-pressure upper surface. This curling motion forms a wingtip vortex. Behind the aircraft, each wingtip leaves a rotating tube of air. The two vortices trail behind the airplane and gradually descend and dissipate. These vortices are not merely a visual curiosity. They are evidence that the wing has spent energy creating lift. They produce a downward motion of air behind the wing called downwash. Now return to the lift vector. In a simplified two-dimensional view, lift points perpendicular to the oncoming airflow, but the wing does not experience only the undisturbed oncoming airflow. It also experiences the downward tilted airflow created by its own wake. The effective airflow direction is tilted slightly downward behind the wing. As a result, the total aerodynamic force is tilted slightly backward. The rearward component of that tilted force is induced drag. The key idea is this: a finite wing produces lift by turning air downward, and that process creates a rearward aerodynamic penalty. The more lift required, the stronger the downwash and the larger the induced drag. NASA induced drag relation expresses the idea compactly. Induced drag coefficient grows with the square of lift coefficient and decreases as aspect ratio and span efficiency improve. 2:1. You do not need to work through the equation, but its meaning is important. Producing more lift tends to increase induced drag sharply. A longer, higher aspect ratio wing tends to reduce induced drag. A wing that distributes lift efficiently along its span tends to reduce induced drag. Why induced drag is worst at low speed. An aircraft in steady, level flight must produce lift equal to its weight. If the aircraft flies more slowly, it must make the same required lift with less dynamic pressure. The usual response is to fly at a higher angle of attack or use more high lift configuration. That means the wing must operate at a higher lift coefficient. Higher lift coefficient means stronger circulation, stronger downwash, stronger wingtip vortices, and more induced drag. This is why induced drag is most important during takeoff, initial climb, slow flight, landing approach, steep turns, heavyweight operations, low-speed gliding, operations at high-density altitude. It is also why flying slowly can demand surprising amounts of power. Many people assume slower always means more efficient, because the aircraft encounters less air each second. That is only partly true. Below a certain speed, the wing must work so hard to hold the aircraft up that induced drag rises rapidly. For a fixed-wing aircraft, there is a region at low speed where slowing down requires more thrust, not less. Pilots call this the backside of the power curve or the region of reversed command. If a pilot slows further while trying to maintain altitude, induced drag rises. More power is needed to keep the aircraft from descending. If the pilot adds power but does not manage pitch correctly, the aircraft can still settle or approach a stall. This is particularly relevant during approaches to landing. The aircraft is intentionally flying near the low speed end of its operating range, with flaps and landing gear deployed. The pilot must manage pitch, thrust, angle of attack, and descent path carefully because the performance margins are smaller. Wingtip vortices and wake turbulence. Wingtip vortices create more than induced drag. They also create wake turbulence. A heavy aircraft flying slowly and producing a great deal of lift generates especially strong vortices. That is why wake turbulence is a serious concern behind large airliners during takeoff and landing. The vortices can persist for some time, sink below the flight path, drift with the wind, and create rolling moments on a smaller aircraft that flies into them. Wake turbulence separation rules used by air traffic control are based on this physical reality. The concern is not just jet blast or engine exhaust. It is the rotating wake left by the lifting wings. A smaller airplane can also create vortices. All finite wings do. The strength depends on how much lift the wing is producing and how the lift is distributed along the span. This gives a useful way to connect aircraft size, speed, and wake. A heavy aircraft needs more lift. A slow aircraft must produce that lift at a high lift coefficient. High lift coefficient creates strong downwash and stronger vortices. Strong vortices mean more induced drag and greater wake turbulence hazard. The wake is therefore a visible reminder that lift has an energetic cost. Aspect ratio. Why long wings are efficient. Aspect ratio is a measure of wing slenderness. A simple definition is wingspan squared divided by wing area. For an intuitive picture, imagine two wings with the same area. One is short and wide, like a stubby rectangle. The other is long and narrow, like a glider wing. The long, narrow wing has a higher aspect ratio. High aspect ratio wings reduce induced drag because they spread lift over a greater span. The pressure difference near any one tip has less influence over the overall wing, and the wing can produce the required lift with weaker induced flow. That is why sailplanes have very long wings. Their mission is to travel as far as possible while losing as little altitude as possible. Minimizing induced drag is central to that goal. Many airliners also use relatively high aspect ratio wings because long-range cruise efficiency matters greatly. Modern airliners often use winglets or rake tips to improve the flow near the wingtip and reduce the strength of the vortex system. But long wings are not automatically better. They create structural and operational challenges. A longer wing bends more and may require more structural weight. Longer wings can create aeroelastic issues, such as flutter. Airports need wider gates, taxiways, and parking spaces. Long wings may be inconvenient for storage, transport, shipboard operations, or forested field sites. High-speed aircraft may prefer lower aspect ratio or more sweep for other aerodynamic reasons. A fighter aircraft, for example, may accept a lower aspect ratio because it prioritizes compactness, high-speed maneuvering, structural strength, and supersonic performance. A carrier-based aircraft may use folding wing tips to fit aboard a ship. A small multirotor drone does not rely on fixed wings at all while hovering, though some hybrid drones add wings to improve forward flight endurance. Every configuration reflects a mission trade, lift distribution and span efficiency. Not all wings use their span equally well. A wing produces less induced drag when the lift is distributed in a way that minimizes wasted energy in the wake. The idealized target is often called an elliptical lift distribution. This does not necessarily mean the wing itself must have an elliptical outline. An elliptical-shaped wing can help create this distribution, but twist, taper, airfoil choice, flap design, and operating condition also matter. The famous World War II Supermarine Spitfire had an elliptical wing platform, but modern aircraft often achieve good span efficiency with tapered wings, swept wings, winglets, and other design features that are easier to manufacture or better for the overall mission. The broader concept is span efficiency. A wing with high span efficiency generates less induced drag for a given amount of lift, wingspan, and wing area. It makes better use of its available span. Winglets are one familiar attempt to improve span efficiency. A winglet is an upward, outward, or otherwise carefully shaped extension near the wingtip. It does not simply stop the vortex. The vortex cannot be eliminated as long as a finite wing produces lift. Instead, the winglet changes the local flow and can reduce the induced drag penalty by improving how the wing interacts with its tip flow. Winglets are not free. They add weight, bending load, manufacturing complexity, and sometimes drag in off-design conditions. Their value depends on the aircraft's mission. They are especially attractive when designers want some of the benefits of a longer wing without increasing wingspan enough to cause airport gate problems. The drag polar. Why every aircraft has an efficient speed. If we could draw a graph, we would usually show parasite drag rising with speed and induced drag falling with speed. The sum forms a broad U-shaped curve called the drag polar in its performance sense, or more precisely, a total drag curve. But this lesson does not need a graph. Picture the trade-off in words. At very low speed, the aircraft needs high angle of attack to make enough lift. Induced drag is high. Parasite drag is low. Total drag is high because induced drag dominates. At very high speed, the wing can make required lift at a low angle of attack. Induced drag is relatively low. Parasite drag is very high. Total drag is high because parasite drag dominates. Between those two extremes is a speed where total drag is at its minimum. At that speed, the aircraft gets the greatest amount of lift for the least amount of drag. This condition is called maximum lift-to-drag ratio, usually written as. NASA describes lift-to-drag ratio as a measure of aerodynamic efficiency. In gliding flight, a higher corresponds to a shallower glide angle and more horizontal distance traveled for a given loss of height. For a glider, maximum is a central performance condition. A glider within a 40 can, in still air, travel roughly 40 units forward for every 1 unit of altitude it loses. A lower performance trainer aircraft might have a much smaller glide ratio. The exact number depends on aircraft type, weight, configuration, and conditions, but the principle is universal. High means aerodynamic efficiency. For powered aircraft, matters because it generally corresponds to minimum thrust required. It is often associated with best glide speed in an engine-out situation. It also informs range and endurance planning, though the exact most efficient speed depends on whether the aircraft uses a jet engine, propeller, electric motor, or another propulsion system. The point is not that every flight should occur at maximum. Airliners fly faster than their absolute minimum drag speed because schedules, weather, air traffic flow, engine efficiency, and economics matter. Fighters fly much faster because their mission requires it. Drones may fly at a speed chosen for sensor coverage or communications range rather than pure aerodynamic efficiency, but gives a useful benchmark. It is the condition where the airframe itself is doing the most with the least aerodynamic waste. Drag and aircraft mission design. Different missions push aircraft toward different drag compromises. Gliders. Gliders are built around high lift-to-drag ratio. They have long wings, smooth surfaces, narrow fuselages, retractable landing gear where practical and minimal external protrusions. They fly relatively slowly and avoid wasting energy. A glider's shape communicates its mission immediately. It is optimized to preserve altitude and cover distance without engine thrust. Airliners. Airliners must combine good cruise efficiency with takeoff and landing performance, passenger volume, structural durability, safety, maintainability, and airport compatibility. Their wings are designed for efficient cruise, often with sweep for transonic speeds and high-lift devices for landing. Their engines are mounted in carefully shaped nacelles. Their landing gear retracts. Their fuselage is large enough to carry people and cargo, but shaped to reduce drag as much as practical. Airliners also use a lot of design effort to reduce incremental drag. A small improvement in fuel burn matters enormously when multiplied across thousands of flights. Fighters and high-performance aircraft. Fighters often accept higher drag because they are optimized for speed, acceleration, maneuverability, rapid climb, payload flexibility, and sometimes low observability. External weapons, fuel tanks, sensor pods, and control surfaces may add drag, but they serve mission needs. High thrust can compensate for aerodynamic inefficiency when necessary, though at a fuel cost penalty. Supersonic aircraft face additional drag from shock waves, called wave drag. Their shape must manage not only ordinary parasite and induced drag, but also the effects of compressibility. That is why they tend to have thin, swept, or delta-like wings and carefully shaped fuselages. Small drones. A multi-rotor drone usually accepts very high drag because it is designed to hover, take off vertically, hold position, and maneuver in confined spaces. Its arms, rotors, landing legs, cameras, and battery packs may be aerodynamically untidy, but the mission values mobility over cruise efficiency. A fixed-wing drone has a different design logic. If the goal is long-duration mapping, surveillance, or environmental sensing, the aircraft may use a high aspect ratio wing and a slender fuselage, much like a small glider. If it also needs vertical takeoff, the added rotors and mechanisms create drag and weight. The final design reflects which capability matters most. When drag is helpful, It is easy to speak as if all drag is bad. It is not. Aircraft sometimes need drag for control, safety, and operational flexibility. During descent, an aircraft may need to lose altitude without gaining speed. Speed brakes and spoilers add drag deliberately. Landing gear and flaps also add drag, which helps an aircraft descend steeply while maintaining a safe approach speed. After touchdown, spoilers reduce lift and increase drag, helping put more weight on the wheels so the brakes work effectively. Reverse thrust adds another braking mechanism for many jet aircraft. Parachutes are nearly pure drag devices, but they are extremely useful when the goal is to slow an aircraft, spacecraft, test vehicle, or recovery capsule safely. Even a fighter may use an air brake to slow quickly before maneuvering or landing. So the goal is not minimum drag at all times. The goal is to minimize unwanted drag in cruise and to create controllable drag when operations require it. Configuration drag. Why airplanes change character. An aircraft's drag is not fixed. It changes dramatically with configuration. A clean airliner in cruise has landing gear retracted, flaps retracted, slats retracted, and spoilers down. The flow is relatively smooth, and parasite drag is minimized. During approach, the aircraft may extend slats, flaps, landing gear, and possibly speed brakes. Each of these changes increases drag. Some also increase lift or maximum lift. The aircraft becomes a different aerodynamic machine, optimized for slow, controlled descent and landing rather than fast cruise. A small airplane demonstrates the same idea in a simpler way. Extending flaps increases lift and drag. Lowering the landing gear adds substantial parasite drag. The aircraft can then descend more steeply at a manageable airspeed. This is called configuration drag, drag associated with the aircraft's current arrangement of movable surfaces and equipment. Pilots learn to anticipate it. Extending gear too early can require extra power. Extending flaps too early can prevent acceleration if a go-around becomes necessary. Retracting flaps too quickly after takeoff can reduce lift and cause the aircraft to settle. The airplane's configuration must match its energy state and flight phase. Drag, fuel, and environmental impact. Drag directly affects fuel use. If an aircraft has more drag at cruise, its engines must produce more thrust. More thrust generally means more fuel burned. For commercial aviation, even tiny reductions in drag can produce meaningful savings over a fleet's lifetime. A revised fairing, smoother panel joint, improved wingtip, cleaner engine nacelle, or more efficient surface coating may save only a small amount of fuel on one flight. Across thousands of aircraft and millions of flight hours, the savings can be substantial. Reducing drag also reduces the energy needed for a given mission. That can lower carbon dioxide emissions for fuel-burning aircraft and extend range or endurance for battery electric aircraft. But drag reduction itself can carry trade-offs. A complex movable wingtip may improve cruise efficiency but add weight and maintenance burden. A very smooth laminar flow wing may be difficult to preserve in everyday airline service. A fully retractable landing gear system reduces drag but adds mechanisms, doors, actuators, inspection needs, and possible failure modes. The right choice is not always the lowest drag choice in isolation. It is the best balance across fuel use, cost, reliability, safety, maintenance, and mission performance. A practical mental model. When you look at an aircraft, it helps to ask two questions. First, what drag comes from moving this aircraft's shape through the air? That question points you toward parasite drag. You can look for exposed gear, blunt shapes, external equipment, rough surfaces, gaps, antennas, large frontal area, and awkward junctions. Second, what drag comes from the aircraft needing to make lift right now? That question points you toward induced drag. It becomes especially important if the aircraft is heavy, slow, climbing, turning tightly, or flying at high angle of attack. A lightly loaded aircraft cruising quickly at altitude may have low induced drag, but substantial parasite drag. A heavy aircraft climbing slowly after takeoff may have high induced drag even though it is not moving especially fast. The same aircraft can move from one drag regime to the other during a single flight. That is why pilots, engineers, and flight control systems all need to understand drag as a changing condition rather than a single number. Key takeaways. Drag is the rearward aerodynamic force that resists motion through the air. Total drag is usefully divided into parasite drag and induced drag. Parasite drag includes skin friction drag, form drag, and interference drag. Parasite drag rises rapidly with airspeed, approximately with the square of speed. Induced drag is the cost of producing lift with a finite wing. Wingtip vortices and downwash are part of the mechanism that creates induced drag. Induced drag is greatest when a wing must make a lot of lift at low speed, such as during takeoff, landing, climb, and steep turns. High aspect ratio wings reduce induced drag, which is why gliders use long, slender wings. Winglets can improve span efficiency, but they add weight and complexity. Every aircraft has a speed near minimum total drag and maximum lift-to-drag ratio. High means the aircraft produces a lot of lift for relatively little drag and can glide farther for a given loss of altitude. Drag is not always unwanted. Flaps, gear, spoilers, speed brakes, and parachutes create useful drag for descent, landing, and control. Aircraft design is a series of drag trade-offs shaped by mission requirements. The next lesson, 1.5 Wing and Aircraft Geometry, examines how wing span, aspect ratio, sweep, taper, twist, dihedral and wing placement shape efficiency, stability, stall behavior, structural weight, and high-speed capability.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.